The concept of frames of reference is actually a really profound thing. What it's saying is that there's no absolute meaning to being at rest or being stationary. It means, and you've seen this already, that the description of an object's motion depends entirely on the observer's frame of reference. Hopefully you've got a kind of a gut feeling for dealing with frames of reference problems from the previous video. I just wanted to add a little bit more of a mathematical or vector treatment to that, so you know how to solve more complex problems. I'm going to write down an equation which may at first glance look a bit scary. But there's no need to be frightened. This equation just says that the velocity, for velocity frames of reference problems, the velocity of P, some object P relative to object Q, is just the velocity of P minus the velocity of Q. And the trick is that this velocity of P and velocity of Q need to be relative to some common reference frame. Of course, you don't always have to use this equation. This can sometimes be done by using the common sense method, but I'll show you a couple of examples. I'm just going to make a small adjustment to this equation. I'm going to put it relative to some reference frame A. Just say we had the airspeed problem that you saw in the previous video. So let's say we have the velocity of the plane relative to the air. And remember, that was the airspeed. The plane relative to the air was the airspeed. And just say we also have the velocity of the air relative to the ground. And we're trying to find the velocity of the plane relative to the ground. Remember, these are vectors, so we can draw them as such. Here's our plane travelling at 100 kilometres per hour. The velocity of our plane relative to the air, that is. And we're defining the up direction as positive. So there's my vector. I also have the velocity of the air relative to the ground, which is negative. What I need to do is find a relationship between these things so I can find the velocity of the plane relative to the ground. So what I'll do here is say the velocity of the plane relative to the air, so the airspeed of the plane, equals the velocity of the plane relative to the ground minus the velocity of the air relative to the ground. That's just the same as that equation that we have up the top there. This is a vector equation, and we're trying to find the velocity of the plane relative to the ground. So all we need to do is rearrange this equation. And here's where this seemingly kind of complicated equation and funny looking vectors all come back to how it works out in common sense. If we take, again, our velocity of our plane relative to the air, and we add to it, top to tail, the velocity of the air relative to the ground, just as this equation says to here, our final answer will be from the beginning of the first vector to the end of the second, and that will be the velocity of the plane relative to the ground. And if you look at the sizes of those vectors, this was of course 100 This was 80 going down, it was in the negative direction. Slightly not to scale, this diagram, I apologise. This velocity of the plane relative to the ground will obviously be 20 kilometres per hour. Which, as you saw in the previous video, you can do using the common sense method. So here's a fun problem, a classic kind of problem, which is a little bit more complicated, and it's in 2 dimensions. Just say you have a river and the water is flowing up the page like that, and the boat, so let's call this the velocity of the water relative to the shore. And we have a boat that wants to go directly across that way at a velocity of boat relative to shore. So this is the way the boat wants to travel. But if the water is whooshing away up the page, then obviously the boat can't point directly across because it's not going to get across to the side of the river. So what we actually want is the velocity of the boat relative to the water. And from looking at our original equation, you can see the velocity of the boat relative to the water is the velocity of the boat relative to the shore minus the velocity of the water relative to the shore. So there's your common reference frame, is the shore. So now we have a vector subtraction. Watch this, this is cool. How do we subtract vectors? Well, do you remember that we don't want to subtract vectors, we want to add vectors. So what we do is we add the negative of the vector. And how do we do that? We draw the velocity of the boat relative to the shore, and we add to it the negative of the velocity of the water relative to the shore. And negative just means we turn it around. So here's our velocity of the water relative to the shore. All we need to do is add it, the negative of it. Add it down here. Top to tail, negative. So this is negative velocity of the water relative to the shore. Fantastic. We have just added those 2 vectors. So to find the resultant, we go from the beginning of the first to the end of the second, and that is our resultant. That will be our velocity of the boat relative to the water. Sorry for that being in the way there. Now let's stop and think if this makes sense. If I were in this boat and the water was going up the page like that, then what would I need to do in order to head straight across to the opposite side of the river? I would need to point down into the direction of the water, so in the opposite direction of the water, in order to counter some of that velocity from the water. So that is consistent with our final velocity here, which is pointing down the page like that. So that is the velocity that the boat would need to go relative to the water in order to end up going straight across to the opposite side of the shore. I tend to resort to this type of calculation when I'm dealing with a kind of a complex 2-dimensional problem like this. You might find that the common sense method makes more sense to you. So when you get a little bit of practice, you'll see what works best for you. And we'll do lots of problems like this, lots of practice in class.